Welcome to the On My Workbench channel.
This is my new 1.2 meter prime focus satellite dish, tuned specifically for GOES 19. In this video, I'm going to show you how I acquired it, how I modified the feed system, and demonstrate just how incredible the performance is as a GOES Earth station.
When it comes to GOES reception, the holy grail is getting your Viterbi error rate as low as possible. The Viterbi number is essentially a counter showing how many data errors per second the algorithm has to fix. A lower number means a higher signal-to-noise ratio. If your signal-to-noise ratio is high, the data arrives clean. If it's low, the algorithm works overtime to patch the holes. As you can see here, we are hitting Viterbi numbers in the range of 22 to 24, which is absolutely outstanding. The Viterbi algorithm works on the raw stream of bits coming from the satellite, the ones and zeros, before they are even assembled into data packets. The fewer bad bits we receive, the less work the system has to do. This makes the Viterbi number the ultimate tool for tweaking your system. Put simply, the lower the number, the better your station is tuned. I emphasize SNR because it is the single most important metric. A Viterbi number under 100 is generally considered good, but if you can get that number down into the low 20s, like we have here, your system is absolutely smoking. Today, I'm going to show you exactly how I achieve this, not just one, but on two different GOES 19 satellite systems. Of course, the first requirement is a good dish. In radio physics, size matters. I would love to use an 8, 10, or even a 12-foot dish, but those are becoming impossible to find on the used market, and a new one too cost-prohibitive for me. However, I found this 1.2-meter dish online, and I actually bought 3 of them, 1 for this project and 2 for spare parts, just in case. Last year, I built a system for GOES 16 using a 0.9-meter offset fiberglass dish I rescued from going to the scrapyard for $50. Since then, NOAA has shuffled the fleet. GOES 19 moved to the east position in April 2025, becoming the primary satellite. My system made the transition seamlessly. The RF chain consists of a NOAA Sawbird Plus GOES Premium, which acts as both a filter and an ultra-low noise amplifier. It is centered on 1688 MHz. That feeds into a NOAA NESDR Smarty XTR, that is enclosed in an aluminum case for thermal stability. For the cable run, I'm using 24 feet of LMR 240 Ultraflex to keep signal loss to a minimum. For the feed, I decided to build my own waveguide feed horns from scratch. I started with 2 pieces of aluminum pipe, one 6 inches long, the other 12 inches. Both have an outer diameter of 127 millimeters and an inner diameter of 116 millimeters, which is near perfect for this frequency. Robert, a friend of mine in California, actually sent me the pipes and loaned me his vector network analyzer so I could precision tune the feeds for 1.6941 gigahertz. Originally, I tested both the 6-inch and 12-inch versions with an impedance matching cone. The 6-inch version performed significantly better, so I cut the longer pipe down to match it. With the cone set up on the 0.9-meter dish, at times, I was seeing the Viterbi numbers as low as 19. This past October, Robert tipped me off to a sale on these 1.2-meter prime focus dishes for $99 with free shipping. Even though the price has drifted up to around $119, it is still an excellent value for a dish of this aperture size. A link will be in the description. Since this dish was originally designed for C-band, I needed a way to mount my custom-built waveguide to it. I took an existing C-band to 2.4 GHz adapter plate that I had and had my local machine shop fabricate a new version with a larger 180mm outer diameter and a precise 125.5mm diameter hole in its center. I also had the machine shop turn down the front of the waveguide from 127mm to 124mm, extending back exactly 4 centimeters. This creates a lip that acts as a depth stop. Since this dish has a focal length of 456 millimeters, I calculated that the feed needed to protrude exactly 4 centimeters through the plate to hit the focal point. The machining was spot on.
Once mounted, I used a simple hose clamp on the dish side of the adapter. This holds the feed securely against the plate so it won't slide out, but it allows me to rotate the feed by hand. This is critical for adjusting the skew to dial in the linear polarization.
Now, I have to talk about the mount. While the dish itself is great, the mount leaves a lot to be desired. It uses a friction ring base bolted to the concrete. To adjust the azimuth, you have to loosen the anchor bolts that hold down saddle clamps and physically drag the ring across the concrete. After loosening the anchor bolts, I used a rubber mallet to gently tap on the mount to get it to move clockwise or counterclockwise.
Honestly, it's a poor design for doing precision dish alignment. The friction makes fine-tuning incredibly frustrating. The elevation adjustment is slightly better. It uses a telescoping bar, but you still have to manage the weight of the dish with one hand while tightening the bolt with the other. Just a heads up, make sure your frame bolts are snug before you start aiming, or the dish will flop around.
For the software side, I'm running SatDump version 1.22. Here are my settings. Frequency is 1.6941 GHz, sample rate 2.048, and LNA gain at 1.5. Both AGC and Bias T are checked.
When you click the Start buttons, you are looking for two things: a slight hump rising out of the noise floor above the waterfall, and the BPSK constellation diagram. If the constellation looks like a blurry cloud, check your aim. As you peak the dish, those blurry clouds will tighten into two distinct groups of sharper dots. Once I verified and peaked out the satellite signal the best I could using the laptop, I switched over to a Raspberry Pi running Go's tools. Since the text on the Raspberry Pi terminal screen is tiny and hard to read while standing at the dish, Robert wrote a custom piece of software that displays the Viterbi error rate in a large horizontal bar graph. This tool is a lifesaver. If the bar is full to the right, your signal is bad. If it's full to the left, your signal is excellent. It creates a real-time visual feedback loop that makes pointing the dish much easier. Once the dish was peaked, I wanted to see if I could beat the performance of the 0.9 meter offset feed dish, so I used Google AI Studio to analyze my feed geometry. The AI suggested that instead of a cone, I should use a planar scalar ring. Basically, it's a flat metal disc at the front of and flush with the opening of the waveguide feed horn to reshape the beam. I built a prototype planar scalar ring out of stiff plastic sheeting, cut into a 211mm diameter disc with a 125.5mm hole in its center so it would fit over the mouth of the feed. I covered the front face of the scalar ring, the side that's facing the dish, with aluminum foil duct tape. It's critical that the foil is on the front, otherwise the plastic's dielectric constant could detune the ring. The AI also recommended mounting this flush with the feed opening. The results were immediate. My Viterbi number dropped from 39 down to the low 20s. One final observation. For this test, I didn't have a long enough length of LMR 240 cable to reach from the dish location to my workbench, so I used 45 feet of standard TV grade RG6 coax. Even with the cheaper 75 ohm cable, the signal is rock solid, proving that the gain of the dish is doing the heavy lifting. One more thing, and this is very important. After installing the scalar ring, the AI recommended that I reset the 456mm focal length so it was 6mm inside the mouth of the feed. That's the setup. All it took was the fabrication of a good feed horn in a planar scalar ring, along with some patience with the dish mount. Even though the 1.2 meter dish did not beat the 0.9 meter offset dish, its performance still speaks for itself. The AI did not like the inside dimensions of the pipe that I used to fabricate my waveguide feeds, so it provided me with a new set of dimensions to use to fabricate a new waveguide feed. The AI thinks, with the new feed horn design, this 1.2 meter dish could outperform the 0.9 meter dish, so please check back for that video, and thanks for watching the On My Workbench channel.